Here's our first reaction stoichiometric calculation. It's a mass-mass sample problem, and it reads as follows. How many grams of stannous fluoride are produced from the reaction of 30.0 grams of hydrogen fluoride with tin? Before we even attempt the solution, let's make sure that we have the usual materials available. That would be something to write on, something to write with, handout of common oxidation numbers, periodic table, and of course a calculator. First thing we're probably going to need to use is that handout of common oxidation numbers, because you'll notice I haven't given you the formula of anything in the problem as stated. So I'm interested in how many grams of stannous fluoride. So the first step in the solution here is going to be to determine what is the formula for stannous fluoride. The handout of common oxidation numbers would indicate that stannous is 10 with a +2 charge. Fluoride in the lower left-hand corner, F minus 1. If we abide by the single rule of formula writing, the sum of the oxidation numbers must equal 0. Then our formula for stannous fluoride is SNF2. And you'll notice it's down here in the equation right there. It is our first product. And what I will typically do when I know what it is I'm looking for, I put a question mark over it. So that's what I'm looking for. That's where we're going to end up in this calculation. Where are we starting? Well, it says how many grams of stannous fluoride are produced from the reaction of 30.0 grams of hydrogen fluoride. Hydrogen, H plus 1, fluorine, F minus 1. So my formula for hydrogen fluoride is HF. And since I know that I've got 30.0 grams of it, I'm going to put that right over the formula for hydrogen fluoride. So in other words, I'm going to work a problem that begins with 30.0 grams of hydrogen fluoride, and ultimately I'm going to determine how much stannous fluoride that would allow me to produce. Couple of things before I actually start the mass portion of the problem. We never ever work a problem with an equation that isn't balanced. So the next step I need to take is to balance this equation. And this one's pretty simple. All I need is a coefficient of 2 right here. And that coefficient of 2 is going to become extremely important midway through my solution process. The next thing, since this is a mass problem, is I'm going to need the formula or molecular masses of the substance I'm starting with, which in this case is hydrogen fluoride, and the substance that I want to end up with, which is stannous fluoride. So let's go on and make a couple of formula or molecular mass calculations. Hydrogen fluoride, let's do that over here. H, as always, hydrogen is 1 AMU. I've got one of them in the compound, so that's 1 AMU's contribution. And fluorine is element number 9 on the periodic table. It has a mass of 19 AMU's, so I'm going to include it like this. It does appear one time, and pretty simple calculation. The molecular mass, because hydrogen fluoride is actually covalently bonded, the molecular mass is 20 AMU's. Remember, we're very seldom interested in the mass of a single molecule. We're interested in moles. So for hydrogen fluoride, what that means is 20 grams equals 1 mole of hydrogen fluoride. Let's do the same thing for stannous fluoride. Let's go over here, and 10, which is element number 50 on the periodic table, has as its mass 119 AMU's. It appears one time in this compound. Next is fluorine, which we've already determined is 19 AMU's. And it appears in stannous fluoride 2 times, so that's 38 AMU's. And that gives us a total mass of 157 AMU's. But remember, once again, we're not interested in a single formula unit of stannous fluoride. And notice I referred to it as a formula unit because it is ionically bonded. And we're interested in moles. So 1 mole of stannous fluoride is going to be equal to 157 grams of stannous fluoride. Now we're ready to start the actual mass solution to this problem. Always begin with what you're given, which in this case is 30.0 grams of hydrogen fluoride. 30.0 grams, and I'm going to be very precise here. It's hydrogen fluoride. The more precise you are, the easier it's going to be able to track these calculations. The first step, remember this phrase, when in doubt, convert to moles. So I'm going to convert hydrogen fluoride in grams to moles. 1 mole of hydrogen fluoride is 20 grams. The next step, and I'm just going to keep right on going, I'm not going to crank out an answer at this point and bring it down or anything. I'm going to simply go to the next step. And the next step in all of these problems is something we have referred to as the mole ratio. And this is the only step in the solution where the coefficients from the balanced equation get used. Make yourself that note right now. Only in the mole ratio do we use the coefficients from the balanced equation. We've got moles of hydrogen fluoride here. What the mole ratio does is allows us to get from moles of the starting material, hydrogen fluoride, to the moles of the material we want to end up with, the substance, in this case stannous fluoride. So what's the ratio? I've got 2 moles based on the coefficient right there. I've got 2 moles of hydrogen fluoride for every, well, there's no coefficient right there, so it's understood to be 1. For every 1 mole of stannous fluoride. And hopefully you can see that what's happened here is moles of hydrogen fluoride have canceled out, and I've gone from the hydrogen fluoride that I started with to moles of stannous fluoride. This mole ratio step kind of allows us to bridge the gap, if you will. Well, from that point, can I go from moles of stannous fluoride back to grams of stannous fluoride? And that's where this calculation comes into play. The answer to that, of course, is yes. 157 grams of stannous fluoride is 1 mole of stannous fluoride. And at this point, it simply becomes a matter of pushing buttons on a calculator. My calculator reads as follows: 1.1775 times 10 to the second grams. Okay, and that's stannous fluoride. Let's check our significant figures to complete the problem. 30.0, how many significant figures? Well, it's my hope that by this time you recognize that as 3. So what I'm entitled to in my answer is, of course, 3 significant figures. So what this really is 1.18 times 10 to the second grams of stannous fluoride. So what have we determined here? If I start with 30 grams of hydrogen fluoride and I'm not limited by any other reactant, in other words, I've got plenty of the metal over here, tin, symbolized by capital S, lowercase n, then in this reaction, if things were to work perfectly, I would be able to produce 118 grams of stannous fluoride. This second sample problem allows me to make one new point. It reads as follows: how much chlorine gas will I need to produce 250.0 grams of gold 3 chloride according to the reaction below? Well, first thing we probably want to do is pinpoint exactly what it is that we've got and what we're looking for. How much chlorine gas? So in this particular problem, I'm going to put my question mark over chlorine gas. That's what I'm looking for. How much chlorine? And it says, how much chlorine will I need to produce 250.0 grams of gold 3 chloride? In the event that you can't spot the formula for gold 3 chloride, remember that by putting those Roman numerals there, what I'm telling you is that gold, in this case, has an oxidation number of 3 plus. Chloride, as always, lower left-hand corner of our common oxidation numbers handout, Cl minus. And if we remember once again that the sum of the oxidation numbers must equal 0, then I think you can see I'm going to need 3-chlorine. So my formula for gold 3 chloride is AuCl3, and here it is. It's our one and only product. Well, I've got 250.0 grams of gold 3 chloride. And the reason I show this as our second sample problem is because this time I'm given a mass of a product and asked to determine how much of a particular reactant would be needed to form that much product. In the previous sample problem, it was, okay, if I start with a certain number of grams of a particular reactant, how much product could I produce? So essentially, this problem is reversed. Nonetheless, the solution process is the exact same. What's next? Let's calculate some formula masses. Before I go any further, there's something I haven't done yet that I must do in order to work this problem correctly, especially when it comes time to use the mole ratio step. You know what that is? And if you said, yeah, you haven't balanced the equation, you're absolutely right. I'm going to need a 2 here, a 3 here, and a 2 here. And that balances my equation. You remember why we balance equations? Because if we don't, it's going to appear that we are violating what law? Well, it's the law of conservation of mass or matter. So here we go. Start our solution, our stoichiometric calculation, 250.0. And I cannot drop that last 0 because it is significant. 250.0 grams of gold 3 chloride. When in doubt, do what? Convert to moles. 1 mole of gold 3 chloride has a mass of 303.5 grams. Next step, it's the step that we have a special name for. It's the mole ratio step. It's the one and only step where I get to use the coefficients from the balanced equation. Since I'm looking to go from moles of gold 3 chloride to moles of chlorine, I need to get my moles of gold 3 chloride to cancel out. So I'm going to put them in the bottom. There are 2 moles of gold 3 chloride for every 3 moles of chlorine. And you can see I've been able to move from moles of the starting substance, gold 3 chloride, to moles of chlorine, courtesy of that step. And again, remember, that's the only step where you get to use the equation's coefficients. All right, last step. Convert moles of chlorine to grams of chlorine. Well, there are 71 grams of chlorine in 1 mole of chlorine. And that gives me 8, and remember this is a calculator answer, 8.773 times 10 to the first grams of chlorine. Last thing to check, significant figures. Always go back to what we started with, 250.0 grams. Believe it or not, that's 4 significant figures. So this answer that I've got right here is appropriate. However, for those of you that want to stick to the safety rule of when in doubt, go with 3, it would be 8.77 times 10 to the first grams of chlorine. Here are 2 mass practice problems for you to attempt. The answers are provided for you in red. Good luck.